All right, students, so let's continue on here. The next topic that we're going to look over is identifying the types of bonds between atoms. And so we've got three compounds that we're going to look at. And so the main thing that you want to do with these types of compounds is literally just either draw the Lewis dot structure for the compound, either using the Lewis dots, or you can just generally provide a stick, atom stick drawing. So here I'll do the Lewis dot structure, and then I'll show you a quick way to do the stick drawing. And so here we've got a phosphorus. Phosphorus, if I go, let me zoom in here. And so for phosphorus, what we've got is phosphorus is in group 15. And so being in group 15, what that means for us is that if I subtract 10 from that, I'll get 5 valence electrons for the phosphorus. And so phosphorus here should have the following. So it'll be a phosphorus atom, and it'll have 5 valence electrons, 1, 2, 3, 4, and 5. So you can already see that it has a lone pair at the very top. The hydrogen atom is a little bit different. Hydrogen has 1 valence electron, and so I'll put those in green here. 1 valence electron there. And then there's 3 copies of this, so let's go ahead and draw those 3, and then we'll draw the 3 valence electrons here for each of the hydrogens. Now, phosphorus can have 3 additional electrons added to it, which will give it the -3 charge. And so what will happen is that each of these hydrogen atoms will essentially come in and combine in there. And so what we'll do here is I'm going to go ahead and redraw everything one more time. And so what we've got here is, let me go back one. And so we'll do it like this. And so here the phosphorus would be in the center. And so let's go ahead and put that back. You got your phosphorus with your valence electrons. Here you've got a lone pair. You've got 1, 2, 3. And then each of the hydrogen atoms is going to come in here, here, and here, ultimately giving you the bond here. Now you could draw it like this and just understand that each of these areas here is a bond. And since we've got a nonmetal with a nonmetal, this particular bond here, let's go ahead and identify this in yellow. That bond there is going to be a covalent bond. That's going to be the same thing for the other bond here and here, so we don't need to do it all for each individual one. You could have also represented the atom, you could have also represented it in the following way. You could have actually had, let's move this over a little bit, you could have had phosphorus in the middle, bonded here to a hydrogen, bonded to a hydrogen, bonded to a hydrogen, and on top you would have had the lone pair. So the lone pair is up here. Now remember, if you're looking at geometries, what this lone pair is going to do is it's actually going to cause the bonds, these bonds here, to be pushed down, which will give you a trigonal pyramidal structure overall. But that would be the structure there for the pH3, and each of the 3 bonds is going to be a covalent bond. Let's take a look at the next compound. So the next compound here is H2SO4, and you can see right at the very top here you've got a hydrogen, you've got 2 of them, and an SO4. So if we draw the structure for this compound, we're going to get the following. I'm going to go ahead and draw it over here on the right-hand side. So what you're going to get here is you're going to get a hydrogen. So let's just draw all the structures. You get a hydrogen with 1 valence electron, another hydrogen with another valence electron, and then you're going to get a polyatomic with a sulfur bound to 1, 2, 3, 4 oxygens. Now, what you'll need to do here is kind of go through the process of trying to figure out the overall structure. And you do need to take into account each of the valence electrons for each one. So here for the hydrogen, we already know that we've got 2 valence electrons. But when we consider the sulfur is going to have 16 minus 10, 16 because it's in group 16, minus the 10 gives you 6 valence electrons. And then each of the oxygens is going to have 16 minus 10 as well. Oxygen is also in group 16, so that'll mean 6 valence electrons for each and every one of these oxygens. Notice that there are 4. So what we'll have to do here is we're going to have to say times 4. So that'll give us 24 valence electrons just for the oxygen alone. And so what we'll do at this point is we're going to add the 24, add the 6, and add the 2, and that'll give us a total here of 24 plus 6 gives us 30, plus the 2, and it's going to be 32. valence electrons overall. So what we will need to do is we will need to come in here and put the structure the way we think it's going to be. I had already kind of drawn a structure here. We just don't know how the arrangement of electrons is going to be at this point, but one of the rules is the most electronegative atom is going to get the electrons first so that it can get its octet. So that's what I'm going to start with here. I'm going to put the SO4, bond it to an oxygen, oxygen on top, bottom, and to the right. And so oxygen is the more electronegative atom between sulfur and itself. So we're going to give the electrons to oxygen first. And so I'm going to go ahead and place those in green. So we'll do 1, 2, 3, 4, 5, 6, 7, 8 for the oxygens here. And we're going to go ahead and repeat the same process here for this oxygen, that one, and that one. Now this is what it looks like. And automatically when you get to this part, you're going to notice that you've already placed all of the electrons. There's 8 in this oxygen, 8 in this one, 8 for the top one, and 8 for the right. Right there alone, you've already placed 32 electrons. You have no more electrons to bind the hydrogens. So clearly what we're going to have here is we're going to have a doubling them up, a doubling of the electrons. So you're going to wind up getting double bonds to account for the electrons. And so even though you do have an octet on each of the oxygens and on the sulfur, but what about the remaining hydrogen? So all we really need to do at this point is bring in the hydrogens here at the very end, hydrogen here, and you can see that the hydrogens are already bonded. We can account for that here. In fact, if you would prefer, we can actually draw this in as a bond like that on the left. But I'm going to take that off. But here you know that you've got them all, and so if you double check everything, the hydrogen will have its 2 electrons, which is the lowest number of electrons that you can have in the orbital. So it's got an octet there. So does this hydrogen. Each of the oxygens has a octet, and then if the sulfur in the center, it's got 2, 4, 6, 8. So we do have all the electrons accounted for. This is one version. Other thing that you should know here is that SO4 can actually go through resonance. We'll talk about that later, but for right now, this is the Lewis dot structure for that. Now, what we need to do at this point is consider what is the bond here between the hydrogen and oxygen. Now, you don't need to overthink this, but the bond here between a hydrogen and oxygen is you have a nonmetal bonded to a nonmetal. So this particular bond between these two atoms is going to be a covalent bond. Same thing on the other side, between this nonmetal and that nonmetal, that's a covalent bond. In fact, if you look at the sulfur, for every bond that it forms between itself and oxygen, either to the left, to the right, or to the top, to the right, or to the bottom, all of these are going to be covalent bonds. So let's take a look at the last compound here. We've got another compound. We've got AlBr3. And so Al, aluminum, is actually going to be in group 13. So that means here if I do group 13, minus the 10 means that I'm going to get 3 valence electrons just for the aluminum. And then the bromine here, bromine is in group 17. And so that means 17 minus the 10 means I'm going to get 7 valence electrons for each of the bromine. So when we pair it up here, we'll do an aluminum in the center. And then it's going to have the bromine up top, Br, a Br to the bottom, and a Br to the left. Now already you can tell that you're going to have bonding occurring here. You don't have to go any further. I will finish up the Lewis dot structure, but notice you're going to get a bond between bromine and aluminum. Aluminum is a metal, bromine is a nonmetal, so any bond that forms here is going to result in a ionic bond. And so let's go ahead and finish up here. So we've got 3 electrons from the aluminum, 7 electrons for every bromine, but we do have 3 of them. So what we're going to need to do here is 7 times 3. That'll give us a total of 21 valence electrons for the bromines, plus the 3 of the aluminum gives us 24. So when we place these electrons, we're going to give it to the more electronegative atom. In this case, it's bromine. So that'll be 1, 2, 3, 4, 5, 6, 7, 8. And then we'll do the top 9, 10, 11, 12, 13, 14, 15, 16. And then the last one, 17, 18, 19, 20, 1, 2, 3, 4. Now the reason I drew the ones here in the center like this is because those are the ones that are going to form a bond. And so I'm going to go ahead and denote the bond with a little red line in between. And so this would be the structure of this particular compound. But no matter what, though, the main thing that we're trying to do in this problem is identify the bonds. The bonds here are all the same, so a bond between a metal and a nonmetal, that bond right there is ionic, making the entire compound an ionic compound. Let's go ahead and continue the process here, and our next problem is going to be over here on naming compounds. And so the very first problem in our guide here is looking at what is the name of the following compounds. We've got a total of 5 of them overall that we've got here. So let's go ahead and name these one by one. And so the process is the following. You should use your nomenclature flowchart. I'm going to bring one up to the forefront so you can actually see it, and I'll go through the process of naming each of these. So here is the documents that you're going to need. You're going to need the flowchart, and you're going to need the naming convention. Summarize would be a good one to use. And so we'll go ahead and start out here at the very beginning. So notice here, each of these are compounds, and the first compound has this particular division that I'm making here, because what we're trying to do is identify the first part. So the part that is positive is this polyatomic, which is NH4. Now previously we learned that NH4 is known as ammonium, so this one here would be a compound that would actually use the convention of type 1. Now let's look at it through the flowchart. So we look at the compound, and we start here at the very top. Does the compound begin with a metal or NH4? In this case, the answer is yes. So we know that we have an ionic compound. And then the next thing that we ask is, what type of metal is it? Well, the NH4 is going to follow the case of case 1, like you would name if a metal was in group 1 or group 2. So in case 1, what we need to do is get the name of the cation and then add the name of the anion. So in this particular case, the name of the cation is going to be ammonium. And then the next name is going to come from this polyatomic here, MnO4. Now, if you go look at the periodic table of ions, you should be able to get this name identified. So let's go ahead and look at that now. So here is the periodic table of ions, and the only part that I'm actually interested in is the polyatomic side. So I'm going to go ahead and take that and bring that only to the fore. So if you look for the MnO4, you'll see here in alphabetical order, MnO4 is not here, is right here. So the name is permanganate, and notice the charge is a -1. So when we come over here to the name, we're just going to write that down. And so we would write here permanganate. And so that would be the name right there. Okay, so going on to the next compound, we've got FeCrO4. Again, here we want to distinguish the very first atom, separate it out. That's the positive, and that means that all of this is negative. Notice that we've got chromium and oxygen, so the negative part, the anion, is a polyatomic. We're going to have to go to that polyatomic one more time. But notice here that iron is not in group 1 or in group 2. Iron is actually a transition metal, so what we need to do here is we need to look at the rule for that particular process. So let's take a look at this. So we'll take a look at the compound here. Does it begin with a metal? The answer is yes, so we know it's ionic. What kind of metal is it? Iron is a transition metal, so we have to use case 2. So in order for us to kind of get this, let's bring our items here, move everything aside, and then we're going to look at the naming formats for case 2. And so the naming format here for case 2 indicates that we're going to have to take the name of the cation first, followed by the charge of the ion in parentheses. That will be the charge of the cation, followed by the name of the anion. So let's go ahead and move this out of the way and follow that convention. So in this particular case, we're going to get the name of the metal, which is iron. We do need to find the charge of the iron, so in order for us to do that, we're going to have to look at what the charge of the CrO4 is. And so in order for us to do that, we have to bring in the polyatomic ion chart, so let's do that. So we'll look for CrO4 down the list. CrO4 is right here. CrO4, it's got a -2 charge, and it's called chromate. So we'll put that into the name. And so what that means here is when we write down the name here, we're going to put chromate. And since we know that the chromate is a -2, the charge that iron has to have in order to equal to 0 here is going to have to be a +2 charge. So now that we know the +2 charge for the iron, we can put that in parentheses right there. And so I will put this here. I know I didn't have enough space, but you would put here in parentheses a Roman numeral 2. In fact, let me go ahead and clean this up. And so that's the name now, iron 2 chromate. Next compound is boron with a subscript of 2, Bs3. And so notice here the first atom is boron. This is a nonmetal. The second atom is a nonmetal. So both of these are nonmetals, making this a covalent compound. So if we're looking at the cases here, we can literally just come in here and look at the flow chart and tell us which case we're going to use. So following the cases here, we do know that the compound doesn't begin with a metal and it does not begin with hydrogen. So we have a covalent compound. We're going to use case 4. And so case 4, if we move this out of the way, case 4 means that we're going to have to follow the following rule. Case 4 means covalent compounds. And we have to use prefixes here, but in the prefix at the very beginning, we have to identify how many atoms of the cation there are first, but we're going to use the prefix name. So that means that we're going to have to say either mono, di, tri, or one of those prefixes to account for the number of atoms of the cation, followed by the name of the cation, followed by the prefix or the number of atoms of the anion, and then we're going to finish it off with the name of the anion. Okay, so let's go ahead and do that now. So here the prefix for a 2 is known as di. The prefix for the 3 is tri. The name of the first atom is boron, so we're going to put the prefix first, and so that means for this particular name, we're going to have di followed by the name of the cation, and in our particular case, the boron is the positive atom, so we're going to call it boron. The cation is always the name of the element, so we'll do that there, followed by the prefix of the second atom, which is going to be tri, and then followed by the anion, or name of the anion of that particular element. So in this particular case, sulfur is the second atom, but it's in the negative form or the anion position. So when we name it, we're going to call it sulfide. And so that would be the entire name for that particular compound. Now the next compound is an acid. You can see that already because it begins with H. But just to confirm, let's take a look at the flow chart. And so here is the flow chart at the very top. The compound does not begin with a metal, but it does begin with hydrogen. So that means you have an acid. We have to use case 3. And in fact, if we look ahead here for the H2SO4, we're going to use the same case for the next compound as well. So let's go to bring this out to the side. And in the case here, you can see that we're going to use case 3. And then the name here, depending on whether you have a monatomic or a polyatomic, let me get this all the way through. If you've got a monatomic anion, and here we can clearly see in the compound formula, we've only got one atom here in the negative side or the anion. So if we're naming this, you want to follow the rule. If it's monatomic, which it is, we're going to put hydro at the very beginning. And so in this particular case, we're going to put, well, let's start with the H. That means at the very end, we're going to put the word acid. The next thing we're going to do is we're going to take the second atom in the anion position, and then we're going to name it. And clearly that one there is going to be iodine. But in the negative position, it's not iodine, it's iodide. So we're going to change the INE to IDE. And according to the rules, if you've got iodide, IDE ending, you have to add hydro to the beginning of this word or this name, which I'm going to go ahead and put here. And then once you do that, you're going to have to come in here and replace the IDE. You're going to replace it with IC. So the final name that we've got here for this particular compound is going to be hydroiodic acid. And so that would be the name there. Moving on to the last compound, we've got H2SO4. We are going to use the same format, but what I do want to point out here is that the anion portion of this particular compound, I'm going to go ahead and put a positive here around the hydrogen, and then all of this, I'm going to circle it, all of that is the negative part, which means that it is a polyatomic because you've got two different elements in the anion. So when we go name this, we have to go look for it on the polyatomic ion section. Let's go to bring that up. And so that one there is over here. And you can see it here at the very top. The SO4 is going to be right here. It's called sulfate, and it's got a -2 charge. So what we'll do here is we're going to name, first begin with the H part. Let me move everything up for us in a bit. And so now what we've got is we begin with the hydrogen. And so at the very end, we're going to go ahead and write the word here, acid. And then the SO4, we know that it's called sulfate. And since we know that it ends in ATE, we're going to cross this out and put IC. But here with the main atom being the sulfur, we'll put that as the root here. And then we'll put sulfur. And so the full name, when we're all said and done here, is going to be sulfuric acid. All right, there you go. The next concept that we're going to be looking at is the following. So we're going to move over here and we're going to write some formulas now. So when you're writing formulas, the main thing to remember here is you got to be looking at charges. We can already identify individual atoms by their name. So what we'll do here first is we're going to just translate each of the names here into their corresponding formulas. So when you look at iron, we already know that this is going to be an Fe. And so let's go ahead and write that again. We know this is going to be Fe. And the sulfate, we just saw this compound here. The sulfate was an SO4. Now let's verify that the SO4 is in fact that. So we're going to be looking for sulfate. And so in this particular one, we'll bring in the periodic table of ions. The sulfate is identified right here. And then it's SO4, but notice the charge. It's a -2. So it's important that we write that down. Let's move this to the side. And then the charge here, and I'll put this in red, is a -2 charge for the sulfate. Now, iron has a couple of charges. And so what you want to be able to do here is determine, is my charge going to be a +3 or is it going to be a +2? It depends on which one it is, but it's going to depend largely on the anion. And so we don't know which one exactly it is, but here's the question you need to ask. If I take a 3 and I add it to a -2, will that give me 0? The clear answer here is that it's not. It'll give you a +1. So it cannot be the +3. The answer that we're looking for here is going to be the +4. So, excuse me, the +2. So now that we know that, we're going to go ahead and take this and we're going to put it up top. But here, when you add the +2 to the -2, that's going to give you a 0 charge. So we only need one copy of each one of these atoms and polyatomic. So when we put this together, the final formula that we're going to need here is FeSO4. And so that would be the formula of iron and sulfate when they combine. Taking a look at the next pairing here, we're going to take magnesium and we're going to combine it with nitrate. Magnesium here is a metal, and so magnesium's symbol is Mg. We know that magnesium is in group 2. You can see that right here. And in group 2, it'll have a +2 because it's got those 2 valence electrons. So we'll say +2 here. And then we'll go look for the formula for nitrate and its charge. And you can see already that the nitrate's right here. And it's an NO3 with a -1. So we'll put that down. Here, this is an NO3 with a -1 charge. The problem for us is if I take this +2 and I add it to a -1, that's not going to give me a 0. So what we'll need to do is we're going to need to bring another copy of the NO3. You could do that by doing the crisscross here. Take the 2 bringing on the outside. Since this is a polyatomic, you first want to put that in parentheses. And then you want to bring this 2 on the outside of that. And so we'll put the 2 on the outside here. And then we'll write a clean copy of this. Our clean copy of this formula is going to be Mg, parentheses, NO3, 2. And so here is the formula for magnesium and nitrate when it's combined. And finally here, the last compound that we've got is when we combine calcium and hydroxide. Calcium is located right here in group 2. It's got a +2 charge, so we can start with that. And so what we'll say here is Ca, and it has a +2 charge. The hydroxide is a polyatomic, and this is one of those anions that you want to commit to memory because it's a common one. And hydroxide's right here. And it's got an OH and a formula and a -1 charge. So what we'll need here is going to be a OH and a -1 charge. And like the previous example here, when you add the 2 and the 1, that will give you a +1. So we're going to need another copy of the OH. Since the OH is a polyatomic, I first need to put the parentheses, and then I can bring the 2 on the outside and put it on the outside of the parentheses. Let's clean this up, and our final formula should be CaOH2. And so this is the final formula when calcium and hydroxide combine. The next section that we're going to look at is molecular geometry. Now, there were a number of shapes that you needed to be aware of. I'm going to go ahead and point this out. You should have your molecular geometry sheet in front of you, and if you do, you should use the following. And so here are the geometries that you should be aware of, and I'm going to go ahead and zoom in on this. Here are the geometries that you should be aware of. Linear at the very top. Notice that there are no lone pairs at the center atom. Trigonal planar, which has 3 atoms on the outside of a central atom. No lone pairs on that center atom. There's bent with a lone pair. Trigonal tetrahedral, when you've got 4 separate atoms bound to a center atom, and then trigonal pyramidal. 3 atoms bound to a center atom, and notice that there is 1 lone pair. There's a different version of bent here where you have 2 atoms bound to a central atom, but you have 1 and 2 lone pairs. These first 6 options here are the ones that you should really know. And in order to identify the molecular geometry, what you need to do is to be able to do a Lewis dot structure for each of the compounds. So I've got a couple of compounds here for us to look at, and so let's take a look at those right now. Let's move this out of the way, and so with that, so let's go ahead and take the structures here for the H2O. So you've got a hydrogen with a valence electron, another one, oxygen with 1, 2, 3, 4, 5, 6. The way these connect here is you're going to have an oxygen in the center, 1, 2 electron, lone pair, 1 pair. You're going to get the hydrogen here binding, and I'm going to go ahead and change the valence electrons for the hydrogens as individuals. And here you've got the hydrogen, and you've got the hydrogen. Now there is an interaction here between these 2 electrons right here and right here, but here is the structure. Now what I would do at this point is, yes, this is going to help you, but what I would do at this point is I'm going to say, go ahead and find a way that where you can actually just come in, instead of writing the atom, just go ahead and put a dot for the element. And when you do that, you're going to see that you've got an arrangement here that looks very similar to one of the structures you've already seen. So I've already kind of brought our structures over here, and you can see right off the bat, you've got 1 electron, 1 atom, another atom, another atom. So you've got 3 of them, but here you've got a lone pair up top and a lone pair down below. So you might be tempted to say that this is linear, and in many respects they do look alike, but don't forget that you've got lone pairs. And so what we can do here is we can actually come in and say, for this particular example, it's not going to be that particular version of it. So we can rule that one out. We know also that it's not going to be the trigonal planar because you need 3 atoms around a central atom, and we've only got 2. And so it's not the trigonal planar. And even though here we've got 1, 2, 3 atoms, 1, 2, 3 in the next item, there's only 1 lone pair, and here in our example we've got 2. So it's not going to be this version here, and we can, by visual inspection, we can also rule out tetrahedral and trigonal pyramidal. The only option that remains that actually is viable here is going to be the second version of the bent structure. Notice here we've got 1, 2, 3 atoms, but 1 and 2 lone pairs. We've got 1, 2 lone pairs. So our structure then is going to be here. It's going to be a bent structure. So this is it right here. So we would say that this particular structure here is bent for the H2O. All right, take a look at the next one. I'm going to go ahead and clear out the board. So now here when we look at CH4, what we've got here is we got a carbon atom. It's going to have 1, 2, 3, 4. And then you've got 4 separate hydrogens, each one with their respective valence electron. And so when you combine them, the way that we'll combine them here is you're going to have a carbon in the center, and it'll form hydrogen this way, hydrogen that way, down and to the left. And if we use that method that we did before, we're going to go ahead and put dots around every element symbol here. So we've got 1 dot, 2, 3, 4 up top, And if we look at all of the different options that we've got here, we can actually come up with a determination on what structure we've got. So in this particular case, notice we have a central atom and it has 1, 2, 3, 4 atoms attached. So we can literally come in here and disqualify some of these. We know it's not linear because there's only 2 atoms here, so we can rule this one out. And so I'm going to go ahead and do the following. Let's make this a little bit smaller. We can rule that one out. We can also rule out the trigonal planar because there's only 1, 2, 3 of them surrounding that center atom. We can do the same thing for the bent because there's only 2 attached. We'll come to the third one over here, the trigonal pyramidal. There's 1, 2, 3 atoms in the center. We need 4, so we can definitely rule that one out as well. It's not bent for the same reason. There's only 1, 2 atoms around the center atom, and there's 2 lone pairs. There's no lone pairs in our structure. So the only one that remains here is going to be the tetrahedral right here, and it actually does resemble very closely that structure there. So this particular structure here is tetrahedral. And so that's how you would name that. Let's go ahead and do the final compound here, AsF3, and let's clear out the board. So As, arsenic, is in group 15, so we know that it's going to have 5 valence electrons. So when we actually draw the structure here, we're going to put As with 5 valence electrons. We're going to put 1, 2, 3, 4, 5. And then each of the fluorines has 7 valence electrons. And so that means that when it binds, it'll form a bond here with each of the 3 single valence electrons of the arsenic. And so here you'll have this structure here overall. And then you've got your AF3 or ASF3. So notice here we've got a single lone pair at the top. Let's go ahead and do the thing that we did before. We're going to go ahead and put atoms, circles in there to kind of denote each of the atoms. So there's 1 here, there's 2, there's 3, there's 4. We know that we've got bonds in between all of these, and so here's our bond, bond, and bond. But notice here at the very top, we've got a single lone pair. So when we go down the list here, you can actually see that only one of these is actually going to match up just right, and that means that the trigonal pyramidal is that particular structure. You can see it here, single lone pair at the top, single lone pair here in the diagram to our right. So this one here is going to be trigonal pyramidal. Just like that. And so that'll bring that problem to a close. Let's go ahead and look at the next problem down the list. So now what we're going to look at is, let's talk about the polarity of a molecule. Now, this particular section is really just intended for you to be able to identify whether a molecule is going to have a pole. In other words, do you have a distinct positive and a negative side here? So in class, the way I've addressed it is you have a molecule, positive side, which is a cation, and you've got another side that's a negative, or the anion. And there's a clear division between the two. One thing that you can do is you can always put a line between them, and if you've got a division, this is known as a single line test. You can actually identify if you have a distinct charge on one side and a distinct different charge on the other. That would be a successful line test, which would tell you that this particular molecule is going to be polar. So to give us an example here, let's do a couple of compounds that we've seen already. Let's come over to this side, and let's take into account here just a couple. And so I will put on the screen here 2 compounds, and we'll determine if they're both polar or not. All right, so we've got the 2 compounds here. Let's take a look at the one on the right first. We're going to take AsF3. So we know that fluorine is more electronegative than arsenic, so that means that it's going to pull electrons towards it. So this particular electron will be pulled closer to the fluorine, and that would give fluorine here the overall minus charge. And I'm just going to denote it like that. When it does that, it'll give arsenic a positive charge, and so I'll put a plus here. And then we'll do the same thing here for the other fluorine. Looking at along this bond here, that electron will be pulled this way, giving the fluorine here a negative charge as well, and the same thing down below. So overall, if we go ahead and do a line here, you're going to see that the line here, if I do the line right here, notice how I've got a negative on that side, but I've got a negative on this side. I got negatives on both sides, so this is not going to be a polar thing because I've got 3 separate fluorine atoms, and each of them have a negative charge. So you don't have a distinct side that has positive charge and a distinct side that has negative. And so this would be nonpolar. Okay, let's go ahead and take a look at the other compound over here, MgCl2. And for the same reasons here, you've got a magnesium, it's got 2 electrons. This electron on the left is going to be pulled by the chlorine, giving the chlorine atom a negative charge here. So this is going to be a negative charge for the chlorine. It'll be the same thing for the other side. But the charge here for the magnesium, since it's losing both of these 2 electrons here and here, that'll give magnesium a +2 charge. And so what that's going to do here is it's going to give you the situation where if you come and put a line here between these two, you're going to see that you got negative on one side, you've got negative on the other. Even though you do have a positive on the other side, you do have a negative on the right side. So that's going to be a bad scenario there for us. The other item that we can do is if we were to move this other line over here along this row, it'll be the same exact thing, but at opposite, you're still going to get negative charge on both ends. So the magnesium chloride here is a non-polar structure as well. Even though that this particular compound here is going to have a metal and a non-metal, this would be an ionic compound overall because this is an ionic bond. What's going to happen here with this particular compound, though, it'll form ions in solution. So even though it's non-polar, maybe perhaps in solid form, in solution it would be an ion. So that's how you determine polarity of a molecule. Let's go and look at the next problem here. The next problem is a percent composition problem. And the formula for the percent composition can be determined by the following. So what you're going to do is you're going to take the percent composition is going to be equal to the mass of the part that you're interested in divided by the mass of the whole. And we're going to take that number, whatever that is, and we're going to multiply it by 100. And so we'll do that for each of these. But whenever we're doing these kinds of problems, the percent by mass is going to be asked how much mass of each individual atom is the percent for that atom relative to the whole. And so typically with each of these problems, the one thing that you're undoubtedly going to have to do for every single one is you're going to have to determine the molar mass for the entire compound. That'll be the mass of the whole. And then you're going to have to take that number and then you're going to add the mass of all of the individual atoms in this compound and divide it by that molar mass. So let's kind of set it up this way, and I'll show you step by step how we do that. So what we'll do here is we're going to do this. We're going to come in here, and we are going to essentially say, for this particular compound, I know that I've got hydrogen, and I also know here that I've got oxygen. For the hydrogen, I know I've got 2 copies, and I can tell because of the subscript 2, and I've only got 1 copy of the oxygen. And so what I'll do here is equal. I'm going to go ahead and replace each of the symbols here with the respective mass. I'm going to use a whole number for simple calculation here. I know that hydrogen has a mass of 1, and there's 2 copies here. And so if I do that, that'll be 2 grams of hydrogen in the formula. Going to the next atom, hydrogen here, what we'll do here is replace the symbol of oxygen, we'll replace it with mass of 16. There's only 1 copy, so that gives us a total mass of 16 grams for all of the oxygens in the formula. So what we'll do at this point is we're going to take this section here and we're going to add it together. And when we do, that'll give us a total of 18 grams for H2O. And so this number here is molar mass for that compound. This is what we're going to call the whole. So if I want to know the percentage of the mass that is only for the hydrogen, I need to take the mass of the hydrogen, which is 2, and divide it by the 18. So what I'll do here is I'm going to take this value here, because each of these are the percentages. So I want to know the percent of hydrogen is equal to the mass of all of the hydrogens in the formula, which is 2 grams. And I'm going to divide that by the total mass, which is 18 grams. Notice here the grams cancel. And if I take this number here and I multiply this by 100, the final answer that I'm going to wind up getting here is going to be 11.1%, and this is going to be hydrogen. So this here is my percent hydrogen, or my percent composition for the hydrogen. If I wanted to calculate the oxygens, I will take the same approach here, take the 16, so this is going to be my percent oxygen, and it'll be equal to the 16 divided by the 18. Take this number times 100, and this number overall should be 88.9. And so we'll write that down here at the bottom, 88.9. This is going to percent oxygen. Now the thing here, if you look at this, if I add up the 11.1 and the 88.9, that total there should be 100% of the total mass accounted for. Let's go ahead and do the same thing here for the next compound, which is CH4. What's the percent composition of each atom in this formula? And so we'll do that using a similar method that we did in the previous example. Here we've got a carbon. There's only one copy. We've got hydrogens, and there's 4. And then we're going to take this carbon, replace it with a mass of 12 grams. There's only 1, and then that'll give us 12 grams for the carbons in the formula. Hydrogen has a mass of 1. There's 4 copies, and that'll give us a 4 grams for all of the hydrogen in the formula. We're going to go ahead and add all of these together, and that'll give us 16 grams for the CH4. This number again is going to be the total. This is what we call the whole, or the molar mass. If I want to figure out the percentage here for the carbon, what I'll do here for this is I'm going to say the percent carbon then is going to be equal to the 12 divided by the 16 times the 100, and this number will give us the number there. I'm going to adjust the top part so we can see a little bit better. We'll do the same thing here for the hydrogen, so the percent hydrogen here is going to be equal to 4 divided by the 16 times 100. And so the number for both of these values here, when I look at that, I will have 75% here for the carbon and then 25% of the mass for the hydrogen. Again, if you add these two values together, you're going to get 100%, in which you do. Okay, so that's the percent composition for each of the two atoms here at the very end. So 75 and 25. Let's go and look at the last and final compound in this series, and it's AsF3. So let's move this up a little bit here. Let's move this up, give us a little bit more space, and let's take care of the last compound. So here, using the same format as before, we're going to go ahead and say here we've got one copy of As, and then for the fluorine, we're going to have 3 copies. Replace the symbol with the actual mass. I'm going to be using the exact mass for this example. You should always use exact masses unless you're doing percentages. Sometimes you can round and it'll be fine, especially if you've got multiple choice. But if it's a free response, you want to definitely be accurate with that. So I'll show you the starting numbers first, and then we'll probably round everything. So for the As, the mass is 74.922. We're going to round this to a 75. And then for the F, this mass here is equal to 18.998, and we'll round this to a 19. There are 3 copies of the F, and there's only 1 copy of the As. And so when we do the math here, we're going to end up getting a 75 for the top, and for the bottom here, we're going to wind up getting 57. So what we'll do at this point is we're going to add these masses together, and that should give us here a total of 132 grams for the AsF3. Okay, now this is going to be up top. I forgot to put this, but I'll put this here. This is going to be grams of As, and this is going to be grams of F. All right. Now, if we're trying to go ahead and analyze this, the next thing that we want to do here is figure out what's the percentage of each. So the percent of As is going to be equal to the 75 right up here, the part. We'll do 75, and then we're going to divide that by the total, which is 132 right here. So we'll put 132. We're going to take that and multiply it by 100, and so that'll give us a number there, and that number there should be 56.8% As. And then the other one, percent of the fluorine, the mass of the fluorine is going to be the total mass of fluorines, which is 57 grams. And so that'll be 57 here, and we're going to divide that by the total mass of 132. We're going to multiply that by 100, and the final value that we're going to need here at the very end when we do all the calculation is 43.1. percent, and that is going to be the percent of fluorine. And so when you go through all of these here, you can actually calculate, add that number to this number, and you should end up with 100% overall to account for the total mass.